kaydımıza başladık. Geçen ders tam burada kalmıştık. Genel diferansiyel bir denklem oluşturmuştuk. Şey için adı neydi? Hem inductor circuit için hem kapasitör circuitry için. Buradan devam edecektik. Evet, şimdi başlıyorum. Now, we learned how to solve the natural. Just a second, let me just have something to write on. I need something like a chalk. We kind of learned in the last lecture how to solve a homogeneous part of this differential equation. I also showed how to solve the particular part too, but just it might be a good idea to remind it just before starting the lecture in here. I mean, as a general formula, we have this kind of differential equation we'll have to deal with in this course, in this lecture specifically. I mean, if you just take the VL, or just if you look at here, if you take this part for the inductor circuitry or this part for the capacitor circuitry, I mean, those things are constants. And if you use this, man, we cannot see anything with yellow. Who put yellow over there? Anyway, this portion and this portion, as you can remember from the last lecture, just a second, this portion, are the time constants. So using that and just trying to write in a general format, we can obtain this formulation. It is a variable derivative plus the variable divided by the time constant is equal to a k, a constant. I mean, this is the kind of differential equation we need to solve. And there's the nice thing about it is, if you're just using it to specify a system that we already know. I mean, the system we are working on can be described by using the initial value of the capacitor voltage or inductor current and the final value of them. So we can solve this differential equation using the initial values and final values as we can find them. From the structure, from the physical structure of the system, we can know it's possible for us to determine the initial and final form of the state variable. So, I mean, just think it this way: when the system is completely at a steady state, the derivative of this variable will be going to be 0. And that means this portion, we will be left with this portion of the equation only to find the final value, I'm saying. When the system is at a steady state, there is no change, the derivative will be 0. So we can easily find the final value using this. Knowing the initial value and the final value, maybe we can reformulate the solution of this first order differential equation to find it in terms of the initial and the final values. Let's just try to do it in that manner. I mean, I'll write the differential equation in this form. Just to remind a little bit, it was in this form. I took this portion and took it to the other side of the equation and put a minus sign in front of it. That's what I did in here. I mean, and this was, as we just calculated in the previous law, so that is the final value of the state. So instead of this, I can write the final value. And I can reformulate everything using something like this. And using separation of variables, we just look at these two equations now. Instead of this portion, I'm writing this portion. Let me just put it this way. This portion, man, this portion is replaced with this one. As you can see now, I can take the x dependencies on one side and t dependencies on one side and obtain this. This is called separation of variables in mathematics. I mean, I'm separating the variables, related variables, to the one side of the equation, and other equations to the rest of the equation, to the other side of the equation, inequality, and try to solve it in that manner. Now, integrating both sides, that's what we did before. The thing is, integration will leave us with some initial values. That is the z part in here. When we take the integration of this part, there will be an initial portion due to this integration, another initial part due to this part of the integration. Luckily, we can combine them using something like this. I mean, this is an arbitrary constant, but we need to calculate that anyway. And the integral of dx divided by x minus xf is natural logarithm of x minus xf. We have seen this before. And integral of dt is just t. And we had this 1 over tau multiplicand in front of that. And just when you have that, it will become t divided by tau. There's a minus sign, don't forget about that. And we still have the z. Now, we need to find z to find the actual solution of the system, of this differential equation. And to find z, I mean, just put since you know the initial values of everything, the initial starting time, the initial value of the variable, either the inductor current or the capacitor voltage, we can just put the initial values there, substitute them, and just solve for z. So the value of z will be something like this. As you can see, everything on this equation is x final and x initial dependent. This is x final and this is x initial dependent. And we know how to calculate x final. X final, as you can see, we were able to calculate multiplying by tau by the time constant. And tau for inductance circuits was Vs over L. For capacitive circuits, it was Is over C. And the time constant was R over L or R times C, I mean, depending on the inductive RL circuit or RC circuitry. Anyway, let's go all the way back. Now, when you substitute that into the equation, you can find it in this one. This is Z now. This is the solution of Z we found from the previous line. Now, to find X in here, you got to take which is taking the power of the system respect to the E, and this will be the final solution for X. As you can see in here, similar to what we find in Z, everything is dependent on the initial value of the variable and the final value of the variable. This is the final value. I mean, you don't need to memorize this, but writing it to somewhere will be helpful in most of the cases, most of the examples, or even in the exam. I mean, write it down to somewhere and just you may take a look at it. You don't need to memorize it, but try to follow the steps to learn how we obtain it. But this is, I mean, as I said before, the general solution of a differential equation in this form. I mean, and not all the differential equations can be solved in this form. We know the initial and final values for our system. That's why we can easily go and just say that this is the general solution to that. Now, we can use this in some examples. I mean, this is just a summary of what we did before. The general solution of a first order differential equation in this form can be obtained using this formulation, where x of s is this k times tau. I mean, hope you can remember it. When we are at the steady state, that means the variable x is not changing anymore. Dx of dt does not change. By the way, is anybody asking any question? Can you hear me? I mean, nobody's saying anything. I'm assuming that everything is going okay. Anyway, t of 0 is the initial starting time. X of t of 0 is the initial value of this x variable. Xf is the final value, which we calculated using this. And tau is the time constant. It's very easy to formulate this, and it's very mathematical exercise to find the solution of it using, I mean, this slide is just following this slide, these two slides. It's a really nice mathematical exercise. I urge you to do it yourself. Anyway, let's try to solve a problem in this manner using the formulations we just got in here. Now the problem says we had a switch in the circuitry, and before t is less than or equal to 0, the circuit was at steady state. That means nothing was changing, and the switch was connected to A. That means A means we have this portion of the circuit. We have two separate circuits, and this portion is the part that is related with this capacitor in here. The other portion of the circuitry at before time is less than 0, we can say, is this part. Yeah, I mean this resistor on that time interval is insignificant. I mean the current is passing only through here. Anyway, this is the circuit we should be dealing with for the times before the switch was open. I mean, we were told that it is at steady state. At DC and steady state conditions means this capacitor is open circuit, so the voltage on the capacitor will be the voltage between the points A. Let me just put between this point and this point. That is the voltage across this resistor is the voltage of the capacitor. That will be the initial value of the capacitor when we switch the circuit, when we put the switch from A to B. Anyway, let's try to calculate that. In order to calculate that, it's simple voltage division. The voltage of the source, 60 volt, will be divided between these two resistors. Voltage division means, I mean, you have to multiply with the resistor that the voltage is on and divide by the total resistance, and multiply the whole thing by the value of the voltage source. So VC at time 0 is about 46 volts. We'll use that value for in the second part of our analysis. Now, back. For the circuitry after t is greater than 0 becomes something like this. This portion of the circuitry is now what we have to deal with. The capacitor has an initial voltage value which is 46 volts, and it will be dissipated on this resistors. We have another current source in here, but doesn't matter. It will be as if that there is a voltage source, an initial voltage source, and a current source in this portion of the circuitry, but the value of the voltage will dissipate quickly, exponentially, as we expect. Now, looking at it this way, I can combine these two resistors. Just look at, sorry about that, I couldn't draw it properly. This portion can be turned into a voltage source in series with a resistor. Then these two resistors can be added up to find an equivalent resistance. That's what we did in here. Then we can put it back into the that was the Norton's form, Thevenin, and back to the Norton's form, Thevenin, a source transformation from Norton to Thevenin, then Thevenin to Norton, will obtain something like this. We add up the resistors, then divide that value with the value of, in order to find the Thevenin voltage, we multiply this current with the resistor value. Then going back to the Norton form, we have to divide the overall resistance by the voltage by the total resistance in here. That's what we did in here. It's minus 6.75 milliamps now. That's what we got in here. This portion is what we're really interested in, because we got to calculate the time constant of the circuit using that. There is another nice thing. When everything, just if you look at in here, the circuitry, when we come to the steady state for this circuitry, that means that the capacitor will act like an open circuit. The capacitor voltage will be whatever the voltage on this 8 kilo ohm resistor. So we know the final value of the voltage across this capacitor, which is just 6.75 milliamps times 8. That is 54 volts is what we're gonna obtain at the end of this at steady state for this circuitry. Anyway, just try to remember that we have an initial value for the voltage that is 46 volts. That's plus 46, by the way. And the final value of that will be minus 54 volts. That means that at some point, the capacitor voltage will become zero. Now, the time constant for us is just the multiplication of the capacitor and the resistance. That is 8 kilo ohms times 0.05 that's microfarads. And when you multiply them out, you'll obtain that it is 400 microseconds. That's really kind of fast anyway. Now the general solution, we just found it from our previous slides, how V of C will act on this circuitry is, we know the initial value of V of C, that was 46. We know the final value, that's minus 54, sorry. Just plug in those values, and we know that T minus T0, that T0 is 0 in here, so you don't have to worry about that much. So this is our solution. This is how the voltage across the capacitor will behave. And at some point, as I said before, starting from 48 and going to the minus 54, it will cross the zero at some point. And if you want to find that time, just equate this equation to zero, and try to find T. I mean, this is how you got to do it. Divide everything by 100, both sides of this equation by 100, and take the natural logarithm of it. Then divide by 2500 to find the value of T. Now, I hope this is also clear. It was a very trivial example, but things can get kind of messy when we got more than one switch in the system. Something like this. Now, we have two times in here. One is, let me just put a timeline in here. It's supposed to be a line, but anyway. At time, let's assume that this is 0, that T is equal to 0. Man, it's hard. One switch is turned off. Then at time T equals 50 milliseconds, the second switch kicks in and it's closed. So we have to just analyze the circuitry in a different manner now. Now, before, in three different sections. The first section is this one, when T is less than 0. When the second is here, when T is, I'm so sorry, it's just between 0 and 50 milliseconds, and T greater than 50 milliseconds. There are three portions of this circuitry, and on the first portion, when we are on here, it says that the switch has been closed, S1 has been closed, and S2 has been open for a long time. Long time means that the circuit was initially at steady state. Now, this was the circuitry. Since this was open before, we don't need to worry about this 20k ohm resistor, and this was closed. So this is the circuitry we had let me just put it in this portion. Man, let me just write it like this. I hope you'll understand it. So using this circuitry, we need to calculate the voltage across this capacitor, and it is the voltage on here. Now, to calculate that, let me go here. You need to know the current I cap passing through there. We had 20 micro amps, and just coming from here, that's a 20. That's, let me say I. There's another current in here, I, up 2 dashes in here. I dash is what I need. But I mean, and using that, I'll be able to calculate the voltage across these 2 nodes. I know there are also other methods. I mean, you can just use source transformation to on some manner and try to find the voltage. But using current division here seems to be a nice idea to me, and that's why I use that. And on current division, I mean, you multiply with the other resistance before that's 20, okay, and divide by the total resistance. That's the whole thing, and that's 4 milliamps is passing through here. This I cap is 4 milliamps using that, and 4 times 50K will give you 200 volts. That is at time t equals 0, we were having plus minus 200 volts in here. That is the initial value of V of C. Now let's go here. Now at time t0, we open this, let's clean this up. We open this switch. That switch over there is still open, by the way. Both S1 and S2 are open at between 0 and 50 milliseconds. So the circuitry is somehow will be just something like this. I'm excluding this portion. I mean, just this will be the circuitry, by the way, and I'm excluding this portion because it's not connected to ground. It's floating. So all I have is an RC circuit of this manner, and we have an initial voltage. What was it? 200 volts, and it's dissipating on this 50K ohm resistor. And since there's no external values, external sources, it's just the nature response of this. It will be the nature response of the system. I'm going all the way back here for the nature response, for the summary of the. This is what we have in here. It is this differential equation. Oh, sorry, this differential equation we need to solve. We have a capacitive circuitry. That means it's the final value will be 0. I mean, you can also use the solution, making the final value to be 0. So it's x of t0 times e to the t minus t0 divided by tau. That will be the solution of this. We go all the way. Yeah, that is VC of 0. That was 200. Sorry, multiplied by t minus t0. But this is for only from 0 to 50 milliseconds. At 50 milliseconds, the VC value might not be 0. So after that, the circuitry will become, sorry, let me erase all here. This portion will be open, this portion will be closed. This is the circuitry now. For t greater than 50 milliseconds, gosh, I am bad at drawing. This doesn't even look 50. Anyway, believe me, it's looked like 50. And this is the portion of the circuitry we have. We have 2 resistors in parallel now. So the circuitry had become something like this. There is a new time constant in here. And at 50 milliseconds, if you just calculate the 50 millisecond initial value for the second switching, initial value of the voltage at second switching is 121.35 volts. We just plug it in 50 milliseconds here and just calculate this using our calculator. And equivalent resistance for this circuit is this 50 parallel with the 200K. Our new time constant is now, if before it was, what was it? What was our time constant? 0.1 seconds. It's now 80 milliseconds. The final value, just if you look at the circuitry, there is no external source. The final value of the voltage across the capacitor will be 0. So you can also assume this like a nature response, or just go back all the way in here, find this equation, find this equation, say that the final value will be 0, just plug in the values. Initial value is now what was it, 121 point something? Yeah, 121.31 times e to the t minus, this is, excuse me, t minus, this is 50 milliseconds, don't forget about that, divided by tau. So that is how the system will behave after t is equal to 50 milliseconds. I hope everything is kind of clear, because this is my last slide for this week. Do you have any questions? Huh. I'll stop the recording in here.